Hello. In this video, we are going to talk about present value. Um, I have preceded this video with another one that explains future value, and so I'm going to use the concepts that we learned in future value to kind of work you through this. So for somebody that has not watched that presentation, you should watch that one first because I rely on that one for the explanations in this one. Anyway, so what are we going to talk about? The basic idea behind present value, finding the value today of a payment that you were going to receive in 1 year, the value today of a payment that you're going to receive in 2 or more years, discounting, which is just the reverse of compounding, and so all the same concepts, just a different word. So subannual discounting, superannual discounting, continuous discounting, multi-period payments. If you look at this, you'll see that this is basically all the same cases that we went through for future value. I want to do them this way and do them in this order so that you can get yourself comfortable with the idea that if you know future value, you know present value. It's just the reverse of the math. So, the entire concept of present value is simply the reverse of the future value concept, as I said. In future value, you know how much money you have to invest today and are trying to figure out how much you will have in the future, taking into consideration that you're going to earn interest between now and then. With present value, you know how much you want to have in the future, so you have some future value in mind, typically, and you're trying to figure out how much you should invest today so that you can get that amount, taking into consideration that you're going to earn interest on it. So kind of graphically, if you thought about it, for future value, we start out basically saying, oh, I know my initial amount. I know the date in the future usually that I want this to happen. So year 1, 2, 3, 4, 5, or period, we should say 5 in this example. So we know the number of periods, 5 periods. We know the periodic interest rate, whatever that is. Remember, we talked about this last time. A period can be less than a year, more than a year, equal to a year. Typically, if they don't tell you how long the period is, you assume it's a year, but otherwise it can be whatever. The periodic interest rate is the interest rate that you earn over the period that elapses from one payment to the next. And so, again, if your periods are less than a year, then your periodic interest rate's less than a year. So you know all of that stuff from a future value standpoint, and what you have to solve for are what will the payments be, and what will the value be at the end at time t, or I think we've used n in the past. And keeping in mind that we use some shortcuts so that you don't even need to figure out the individual interest payments. You can just solve for what t will be at the end. Well, in present value, we just reverse the problem. So now you know the future amount, and you know the future date. You know the number of payments again, and the periodic interest rate. So all those same things you knew, but you know the future amount. And now you're asking the question, what should the initial amount be? So nothing else has changed other than that, basically. So since we're just reversing the future value formula, all we got to do, or the effects of future value, all we have to do is reverse the formula. So if you remember, for future value of a single payment, right, we would just say, what's that payment that we're going to make today? And we'd multiply it by 1 plus the periodic rate times the number of periods, and that will tell us what we'll have in the future. So how do we reverse that? Well, again, we start with the formula. Algebraically, I can just divide both sides by this thing, the 1 plus interest rate raised to the n. So I get future value divided by 1 plus rate to the n equals the amount that I'm gonna pay today. Well, that we just rearrange this and put the a over here. That a, that's present value. Okay, so we could just put a PV in there if we want to, but so the present value is just the future value divided by the interest rate raised to the number of periods. So that's it. We've simply reversed the formula to solve for A instead of solving for future value, and that is present value. A little bit of terminology here. When you are solving for present value, sometimes the periodic interest rate is referred to as the discount rate. It's a discount rate instead of a compounding rate. In future value, we call it the compounding rate because you're reducing the future amount at this rate to get it back to the present. And so you're discounting the future value back to the present value. I don't want you to be thrown by that. That is just a terminology thing. The rate gets determined all the same way throughout. Nothing else changes. It's just terminology. So I just want you guys to be aware that when you hear those terms, it's not like, oh, now I have to learn something else. Same thing. All right, so let's work through the cases. Same ones we did last time, but we're gonna know the future value and solve for the present value now. So assume that in a year I want to have $100. How much money would I have to invest today at an interest rate of 6% to have $100 in the future? So kind of going step by step, if at the end we needed to have $100, then I need to basically divide that by the 1 plus the interest rate. I need to have $94.34 today. So if I invested $94.34 today and earned interest on that, the interest that I would earn at 6% in a year would be $5.66. Add those two together, that's the $100 that I need. So you can check it just the same way you do with the future value. You can check this present value calculation. So now we're moving on to the second case that we did before, which instead of just being 1 year is 2 years. So now instead of the 1 year, we want to have $100 at the end of 2 years. So same 6%. How much do we need to have today in order to have that at the end of 2 years? Well, let's see. We're at the end of the 2 years. We have $100. So if we discount that back by the interest rate, then that means that by the end of the first year, we need to have $94.34, which I think was the same thing that we solved last time. And so if we discount that back by the 1 plus the interest rate, we get $89. And that's what we need to have today. And so today, we need $89. Now, mathematically, instead of doing it by the steps, we could use the discounting formulas that we figured out just a couple of minutes ago and go 100 divided by 1.06 squared, and that also equals the $89. And once again, since this is just a couple of steps, you can check it. So if I invested $89 at 6%, it would earn $534 in the first year, and so at the end of the first year, I'd have 89 plus 534. That's the 94.34. So that's what I invest at the beginning of year 2, earn 6%, that earns 566. We solved for that last time, so that should look familiar. We add the 566 to the 94.34, we got $100. So again, nothing new. Everything is pretty much the same. You're just dividing by that rate instead of multiplying by it because you're going backwards in time instead of frontwards in time. Well, what if you extend this out to beyond 2 years? Well, guess what? Nothing changes about what we learned before in terms of our general formula. So at 5, if we want to have $100 in 5 years, how much do we need to put in today at 6%? Ending value is $100. Divide it by 1 plus the interest rate, raised to 5 years. We need $74.73 today. You could just use your more general future value formula that we learned last time to take the 74.73 and figure out, based on the interest rate, how much it will be worth in 5 years, and it would be the $100. Now we get to something that's a little bit different. I mean, nothing's different about the formula, right? It's still present value equals future value divided by 1 plus R over N. But as in the past, when we were doing subannual discounting, you need to think of N as the number of periods, not the number of years. And you need to think of R as the periodic interest rate, not the annual interest rate. So you want to have $100 at the end of a year. To get there, you're going to invest some amount at 1 year for 6%. but the 6% isn't going to be paid at the end. Instead, you're going to get interest payments made each quarter, right? And so with a nominal rate of 6%, you recognize that when I get paid more frequently, that builds interest faster, so maybe I don't need quite as much. Okay? So how much must I invest? Let's see, starting just like we did with subannual on the future value, how many periods do I have? I have 1 year, and there are 4 periods in the year, so I have 4 periods. What's my periodic interest rate? It's my nominal annual rate, which is 6%, divided by the number of periods in a year, which is 4, so it's 1.5% each period, so each quarter. So the present value, we would say, okay, the ending value is $100. So value at the end of the third period is 100. Remember that period's a quarter here. So the ending value is the value at the end of the fourth quarter. Value at the end of the third quarter is $100 discounted back at 1 plus 1.5%. So remember that is 1.015. It is not 1.15. Okay, so you're discounting back at 1.015. So by the end of the third quarter, you have 98.52. Discount that back to the end of the second quarter, it's 97.07. Discount it back to the end of the first quarter, it's 95.63. Discount it from the end of the first quarter all the way back to the beginning of the first quarter, and that's 94.22. So in this case, you need 94.22 in order to get to that amount. Now, if you looked back at the other example, see if I can find that. Right? You need 94.34. You need to start with 94.34 if you were only going to earn the interest once in the year, so no compounding. You only need 94.22 in this example, so that is showing you the benefit of the compounding. In this case, instead of winding up with more money at the end, you just get to start out with less money at the beginning, and that's how you get the benefit of the compounding. Again, second example of this, instead of the subannual just being inside of a year, we're going to go out to 5 years. So imagine that you want to have $1,000 at the end of 5 years. To get there, you're going to invest an amount, so you're going to invest it now for 5 years at 6%, but your interest is going to be made, payments are going to be made at the end of each month. Okay, so same process, how many periods? 5 years times 4 quarters, right? Equals, I'm sorry, times, that shouldn't say 4 quarters. I'll go ahead and fix that right now. Times 12 months. Per year. Equals 60 periods. Periodic interest rate equals the annual rate divided by the number of periods. So equals 6% divided by 12, so it's 0.5% each month. Makes sense. So now your present value is 100 divided by 1 plus 0.5%. So 1.005 raised to the 60th power equals $741.37. And if you again wanted to for yourself solve that, you certainly can by putting in the 741.37 and solving for the future value of that under these terms, and hopefully you'll see that it winds up being $1,000. I seem to have a real problem with this. I don't know why, but we're going to go ahead and fix it. I just, for some reason, can't get all my numbers to line up. There we go. All right. So now we're going to jump to superannual discounting. We talked about that before. Again, nothing changes about the concept of superannual interest payments if you go from compounding to discounting. Nothing changes. We're still using the same formula, still have the same concept of periods here. It's just a question that you're dividing by the interest rate raised to the number of periods, 1 plus interest rate raised to the number of periods instead of multiplying by it. So let's just work through that example. And I'm sort of raising the level of difficulty here of the examples for you so that you can see it applied with maybe some stuff that's a little bit more unusual. So let's just say that now you want to have $1,000 at the end of 9 years. Not 10 years, 9 years, there you go. To get there, you're going to invest an amount for 5 years. Well, again, I don't know why I keep doing this, but I'm just having this problem with some of my stuff, so we'll clean it up here. Perhaps at some point I'll re-record this with it cleaned up. So you're going to invest an amount at 9 years at 6%, with interest payments made at the end of each year and a half. So instead of being at 1 year or 2 years, it's going to be at a year and a half. So how much must you invest? So again, go through our process. How many periods? 9 years divided by 1.5 years per period equals 6 periods. So 6 1.5 year periods. What's the periodic interest rate? It's 1 plus the annual rate of 6%, okay, raised to the number of periods, number of years in a period, right? And all of that minus 1. So our periodic interest rate is 1 plus 6% raised to the 1.5, because it's a 1 year rate and we're gonna earn over a year and a half. So it's 1.06 to the 1.5 power minus 1. So that's equal to 1.0913 minus 1. And so the periodic rate is 9.13%. So now if we plug that in, we've got 6 periods at 9.13% per period. So the present value is equal to the future value of $1,000 divided by 1.913% raised to the 6th power. You see I calculated that out for you. It becomes $591.90. And again, since you've done the future value of this, you can always take the $591.90 and check to see that in fact it's going to wind up being the $1,000 future value. Our last sort of individual payment one, the continuous. Before it was compounding, now it's discounting. Once again, nothing at all changes here when we go from compounding to discounting. I do want to introduce a couple of other terms for you. I think in the future value, I referred to the amount you calculate here is the compounding factor. Okay. I think it is also oftentimes referred to as the effective yield. Now, again, we can't say that it's an annual yield because we don't know what the period is. But we use the term yield sometimes when we're talking about the 1 plus number instead of just the interest rate number. So yield is 1 plus the interest rate. And I think if you were to plug in numbers here, which we'll do in the example, you'll see that when you take the mathematical constant e and you raise it to these powers, you get an amount that's 1 plus something. And again, just like before, when we want to discount using this rate, we will simply divide by this result instead of multiplying by it. So let's say you wish to have $1,500 in 18 months, and you're going to invest an amount today at a nominal rate of 7%, but it's compounded continuously. So how much must you invest today in order to have $1,500 at the end of 18 months? So how many numbers of years, how many periods do you have? You have 18 months divided by 12 months in a year, so 1.5 years. You have an annual nominal rate of 7%. And so the yield that you're looking for, right, for discounting, the effective yield is the e to the rn equals e raised to the 0.07 times 1.5 years, right? So that's your n power. And so that equals e to the 0.0105 power. That's equal to about a little over 1.11. So that would suggest that your periodic rate, which is your rate that you're going to earn over the 1.5 year long period, is 11.7%. So 7% a year, but 11.07% in a year and a half. So if we now just want the present value, we're going to take the $1,500, divide it by 1.107, gets us $13.50. And again, I'll just say this one more time. You could always take the $13.50 and take that as your present value and compound it using continuous compounding, and convince yourself that at the end of a year and a half that would turn into $1,500. All right, now we're going to talk about multi-period payments. I know in the last time we were talking about making multiple investments. This time I'm just going to call them payments. Shockingly, nothing at all has changed about the concept of multi-period payments when we go from compounding to discounting. Just think of it as, before, when we were thinking about it as an investment, right? It was a little bit different because you're putting in money at different points in time, and you're trying to figure out how much you'll have at the end. Here, what you want to think about it as is that you're going to need to take some money out at certain points in time, and you need to know how much you need to put in now in order to be able to take that out in the future. Okay, so the present value is simply the sum of the present value of each of the amounts again. So you do the same kind of math you did on each one of these and each payment, and then just add them up, just like we did for the future value. I don't know why that did that. So let's just assume that you need to make $3,000 payments at the end of each of the next 3 years. Don't know why, but let's just say you do. So you would like to invest an amount now at a nominal rate of 10% to cover these payments. That way you know that you'll have the money come time to make the payments. How much should you invest now? So payment 1, this is the one that'll be paid a year from now. It's $1,000. If you discount it at 10%, it's $909.09. So if you put $909.09 in today, that'll be worth $1,000 at the end of the year, and you'll have that $1,000 to pay the first payment. Second payment, you're going to put in $1,000 discounted at 1.10%, so raised to the second power, so that's $826.45 is its present value. So if you put the $826.45 in today and let it sit in the investment at 10% for 2 years, it will grow to $1,000, and you'll have that $1,000 to pay at the end of year 2. Same thing with the payment for year 3. You're going to discount it back at 1 plus the rate raised to the third power, because it's 3 years from now. And so that's $751.31. So if you invested that amount today at 10%, then over 3 years it would grow to $1,000, and you'd have that money available basically to pay off the $1,000 at the end of year 3. So how much do I need in the account today? I need $909.09, $826.45, $751.31. I need to add all those up. That becomes $2486.85. And that's what I need in order to make those $3,000 worth of payments in the future. Now notice that that's a lot less than $3,000. The $500 difference is the benefit that you got by putting the money in now and letting interest do your work, instead of just waiting and coming up with it as you needed it. That, my friends, is everything that you need to know from our perspective about present value. Again, can't emphasize enough, it's the exact same thing as future value. You're just sort of flipping the math and flipping the concept in terms of what you know versus what you need to figure out. Thank you, guys.